everybody. Welcome to the first webinar for the Rosemont gas chromatographs for 2018. I'm so glad that you guys could all join us today. This will be a high-level view of the Rosemont gas chromatographs, but also the response factors and why they're important. So I thank you for joining. My name is Bonnie Crossland, and I will be your presenter today. Before we begin the presentation, I'd like to take a few moments to familiarize you with the webinar environments. On the screen, you should see a presentation window that's in the center, a Q&A window that's in the upper right-hand corner. This is where you would type in your questions. As you may have noticed, there is no verbal way to ask me questions, so this would be the way we can communicate with each other. Below that, you'll see the speaker bio, so just a little bit on my background. And then below that is a resources related list where we would have documents that we would put if they were related to today's topic. For today's webinar, there are no additional documents that we will have. All the windows that you see can be resized or minimized to suit your viewing preference. Simply point your mouse to the bottom right side of each window to resize the window, or use the minimize control on the upper right. At the bottom of the screen, there's also a collection of icons that can give you additional functionality. If you hover over them, they'll give you a bit of a description of what they are. For example, you can share this presentation over Twitter, you can ask for help questions, or you could click on the icon of the envelope if you had additional questions that you'd want somebody from the Rosemont team to get back to you and answer. Again, if you have any questions during this presentation, feel free to submit them to me using the Q&A window. We have also reserved some time at the end of the presentation, and I'll try to answer as many questions as possible. We are recording this presentation, so for playback for later. For those who are hearing this through a playback or recorded version, you can still submit questions. We have configured the questions to be sent directly to our email address for follow-up. With that, we can begin. So I do see questions on the audio and how do you connect to the audio. The only way you can hear audio is actually through the computer. So if you have your computer on mute, you'll need to unmute that. Unfortunately, that is the only way when we work with ON24, is that the communication is through the computer itself. There is no call-in number that, say, we normally do with a WebEx. So it is all the communication through the computer itself. So hopefully that kind of answers a few questions. So you do need to check your computer to make sure it's off of mute if you are working with a speaker system, to make sure that is fully connected. And I do see somebody said for audio mustn't. There's a couple of questions popping up real quick. Basically, how do we, for audio, for one person must enable Adobe Flash. So maybe we'll give people a few seconds to do that for your particular process. We also have another question. Our piece credit available after this webinar. So I've seen the PDH credit is basically learning credits. We are not doing learning credits for this specific webinar. In fact, we will have 3 other webinars for the year, and there also will not be credits issued. It's just because of the nature of the business. We've had over 700 people register for this webinar, and there was several of you guys also attending live, so we're not able to issue certificates. Even older version of Jones has to get on up. Somebody actually sent an advice from Sergeant, had a good advice. He said he had to enable an older version of Adobe Flash to get the audio video. I'm going to see if I'm going to actually push some of those questions or answers, because obviously if you can't hear me, you're not hearing the solution. So I'm going to see if I can push this one question, push to the slider, see if people can see that. For audio, must enable the flash. I'm going to push another one to the slide area. Another advanced, somebody said they had to use an older version of Flash to hear the audio. And I just quickly let you guys know is how do I get a copy of the recording. That will be done at the end when this presentation ends. The same link that you logged into this presentation will you also be able to use to see the recording. We also will be sending out everybody who's registered a copy of the link that once this presentation or webinar is put up onto the Emerson external portal, we will be sending out a link to everybody who's registered, those who either attended live or those who are hearing a recording. We're getting a couple other questions, and I just want to give people a few seconds to see some of the suggestions people are having about Google Chrome. Yes. So Andrew Peel from ConocoPhillips says Adobe Flash is not compatible with Google Chrome. I know Explorer works the best with ON24. So we'll give everybody a few more seconds to kind of give it a few try to see if they can get the audio connection, and then we'll go from there. I'm just going to, again, let people see what people's other solutions have regarding the lack of audio so we can get that going. Okay. So hopefully people have been able to try various different things and can get connected to the audio. Otherwise, we will start out and continue with the presentation. Oops, sorry. So the agenda today is going to review what is a response factor, then the causes of variation in response, and these are variations that affect all response factors or affect a specific response factor. And then it's those specific issues where it just affects one or two response factors, that's what we're going to use to help troubleshoot some common problems with your gas chromatograph. To relate how important response factors are, there's a couple specifications out there that do reference it. So GPA 2261, which is a common specification that we use on our products, it's basically saying response factors are essential to the accurate determination of the composition of an unknown sample. So we calculate response factors from a known sample, but then we turn around and use that information to help figure out the concentration of an unknown sample. Same thing, ISO 14749 actually has a little bit more details on response factors and their importance. They are critical for the monitoring of the GC for abnormalities with its valve settings, time events, and sample systems. And that's kind of true when we go through our examples towards the back of the presentation. We'll see that how errors with valve setting or time events or even one sampling system can really show up in the response factors. And using that information can really pinpoint what we need to fix. So with that, we will begin with what is a response factor. Using Wikipedia, basically the response factor is a signal produced by the component within a sample, aka the peak area, to the quantity of the component within the sample which produces the signal, the concentration. So basically the response factor formula is peak area over concentration, or calibration concentration. Since that's a bit wordy, we can kind of more simplify that and say that the response is simply described as the response of the detector to the component. And this is regardless of whether it's molar, volume, or mass basis. So the value of using a response factor for a component that was calculated using a known standard, the calibration concentration, is that that concentration of that same component within an unknown sample is then able to be calculated. So if we want an accurate determination of an unknown sample's component concentration, then it's critical the response factor for that component is correct as stated in GP 2261. So reconfiguring that formulation of response factor is peak area over calibration concentration, because response factors are inherent to the material. If we change that around and have the component concentration in an unknown sample, We can take it by the peak area, which we'll get from the GC, divided by that calculated response factor from the calibration. Okay. So one thing we can look at is what is peak area. And in simple terms, it's the area under the curve. It is the signal produced by the component for the Wikipedia definition, and it's proportional to the concentration of that component. It should be noted that peak height instead of peak area may be used for long and flat peaks, so the peak start and end determination may not be reliable. But in generally most cases, we are using peak area. If you have our particular GCs and using our MON software, whether MON 2020 or MON 2000, the peak area and the peak height information can be found in the raw data table, which is accessed through the component data table or the chromatogram viewer. So, previously stated when we were talking about the simple definition is that the response factor is the response of the detector to the component. So in this case, for a thermal conductivity detector, a TCD, the response is the difference in thermal conductivity of the carrier gas. So in this particular example, which is a standard C6 plus example, the carrier is helium, and the components is the difference in thermal conductivity of the carrier gas, helium, to the components, in this case, the C6 plus methanes, aliphanes to the heptanes plus. And again, it's the response of the detector to the difference in thermal conductivity. So basically, in this particular example, what we're looking at is the thermal conductivity of helium, which is 352, compared to methane, which is 78, compared to nitrogen, which is 60. And so what that basically is, your gap between helium and methane is the smallest compared to all the other components, and therefore it should have the smallest response factor. Nitrogen would be next in order, and then ethane, and then propane on the way down. I will say that if you were looking for, say, hydrogen or helium as components of interest, then obviously you wouldn't use helium as your carrier. You would have to find one that has a large thermal conductivity differential. So if your component of interest has a high thermal conductivity, you're going to look for a carrier of a low thermal conductivity. So if it was helium or hydrogen, it would either be argon or nitrogen that we would use as the carrier. Okay. So we'll go back to what we talked about the wiki. We talked about the signal. And so what do we really mean by that? We refer to it, we talked that the signal was basically referred to as the peak area. For a TCD, the signal produces the result of a voltage output being produced. So the TCD consists of basically two matched pair of themistors. So if you look on the left-hand side, you'll see a reference thermistor and a measure thermistor. And so what basically happens is a constant current is applied, 15 milliamps, to the wire, so they heat up. As they heat up, the temperature increases and resistance decreases. But as long as the same material, aka the carrier, is running over the reference and the measure, we have a balanced Wheatstone bridge, and that's your center image. When you combine over the measure side the carrier, so let's say the example, the C6, the helium, with the separated component, say the methane has a lower thermal conductivity, so those two, that mixture combined, will have a lower thermal conductivity than the carrier by itself flowing over the reference. That lower thermal conductivity means that wire's temperature increases more over the measurement. As that temperature increased over the measure increased, the resistance had to decrease, and that causes an imbalance, which causes a voltage differential. So if you look at the formula V equals IR, the current 50 milliamps is constant. So if the resistance changes, the voltage will change. So here's an animation that we have. So in this particular example, hydrogen is the carrier, and then we'll see it come across the screen shortly, methane. And so again, it's the mixture of methane and hydrogen come together that will cause a lower thermal conductivity to go against the thermistor on the measure side. And it's that lower thermal conductivity will cause a change in the temperature which will cause a decrease in the resistance, which will cause a voltage output. So let me run the animation. And so you can see, is it went across the screen, or is it going across the screen, that is causing that peak area. That signal is then that peak area. So we talked about where the peak area comes from. So the next question is, where does the calibration concentration comes from? Well, this one's a little bit easier. The calibration concentration actually comes from your calibration cylinder gas labeled certificate of analysis. And that makes sense, and you can think that the GC is a comparative analyzer. We are comparing against a known standard when we try to measure our unknown standard. And so again, it plays into the formula's response factor is peak area, which we just saw is the signal over the calibration concentration, which again comes from the certificate. So now that we've discussed how you calculate our response factors and where the information comes from, the next question is, where does one find those response factors? And so just to keep it interesting, there's a quick quiz that we should see. I'll give you guys a few seconds. I think this is a pretty straightforward, but if you were looking for your response factors, where would you find them? In the raw data file, the analysis report, or the final calibration report? So I'll give you guys a few more seconds, and we'll see what the results are. I'm just going to quickly read one question to you, and that was, how are the ideal response factors for a cal gas calculated? And so we'll actually go through that later on in the presentation. We will talk about how you get the ideal response factors, and really things we like to look at is the ideal relative response factors. So we'll look at that. Okay, let's look at the results of the poll real quick. And so, yes, okay, pretty good. So we have about 60% people said the final calibration report, and that is correct. And the response factors can be found in the final calibration report. And I do want to spend a little bit of time reviewing this because it's actually a really critical report that gives us a lot of information. Also, it's an FYI, we do have other webinars on our Emerson website that kind of talks about validation of your GC and how to make sure it's operating correctly as well. And there's some more detailed information on the final calibration report and other things that you need to look at. But I do want to go over this because it is critical, and it really is the foundation of helping us understand what can vary with our GCs, and it really is the place where you find your response factors. So on the left-hand side, we see the component name column. So these are your components of interest. These are not necessarily the components that are in your unknown sample or even in your, these are the ones that you want to look at. And these are the ones you're calibrating against. Notice the order that they're listed. They are in the order of elution or retention time. This is the order that the individual components come out of the columns and pass over the detector during the analysis cycle. They're not listed in order of concentration, otherwise methane would be first in this particular example, carbon number, or response factors. They are listed in the order of retention time from the first one out to the last one out passing over the detector. The next column is the calibration concentration column. That is absolutely critical. That's, if you think of it, that actually goes into the formulation or the calculation of the response factor. This is the concentration of the component as found in the calibration gas. So that's what we just talked about previously. These are what comes off the certificate of analysis label that's attached to your calibration cylinder. And again, you can validate them against the component data table. The next two columns are the old and new response factors. Response factors are the individual calibration factors for each component and calculated through the calibration cycle using the analysis cycle. So kind of go back to that formula where if you want to find the concentration of an unknown, it's the peak area that we get from the GC or the signal divided by the response factors that were determined during calibration. And the response factors determined during the calibration is the peak area, again, the signal from the GC, divided by the known concentration of a standard, or basically your calibration gas. This report shows that responses improve association to the O1. If response factors vary more than 10%, there would be an alarm. For those who actually calibrate on a daily basis, it'd be very unlikely to see a 10% variation from one report to the next report. However, for those who may have more of a process application where you more calibrate on a monthly or quarterly basis, it is possible for that alarm to be set. The default is 10%, that you can change that value to whatever you want. If you make it tighter, just be aware that you could have more nuisance alarm. If you make it a greater tolerance for reported alarms, you could be possibly missing shifts that are important to catch. Okay. Next column over is the retention times. And again, it's comparing the old and the new. Again, if you're off about 10 seconds, you will get an alarm. Again, generally you won't see that type of shift if you're calibrating on a daily basis, but you could if you do it again on a monthly or quarterly. The GC itself will make slight modifications, so it saves you guys the effort from every day going back and retweaking the valve timing. The GC will do that for you. I'm just going to quickly answer a few questions we have here. I know that is a heavy hard. What do it means? Oh, C6 to 4. Okay, so somebody had a question on our C6 plus 47, 35, 17. That is the ratio breakout. So what that means is you got 47% C6, 35% C7, and 17% C8. The GC itself, or RGCs I should say, basically have 4 standard ones that you can pick from, lining with your tariff requirements. There's also a custom one that you can put in your own requirements. You can make it 100% C6, you can make it 0% C6, 100% C8. That is what you select yourself as the breakout that you think are your C6 plus, so how much C6, C7, and C8s that you have. So I get the question is the order of response factors correct? The concentration of the standard gas has to decrease in the heavier components. That one I'm going to come back to answer that one. Okay, and the other question I have is how to know what's the time period for calibration of an installed G? Will the DC tell me when to calibrate? So we don't actually cover that in this one. We're going to have a webinar on June 12th on calibration gases, but what's the time period to calibrate your GC? That depends. If you are pipeline, then generally you have tariffs or a specification that tells you what your requirements are. There's also regulatory requirements. Say if you're actually a flare applications, there are EPA rules that tell you how often you have to calibrate. So the GC will not randomly pick for you a calibration time. You need to tell the GC. You can, in most cases, for most applications, set the calibration time per your requirements. It is those requirements that you have to know yourself. They change by application, they change by specification, they change by regulatory, and they change by your own company's procedurals. So there is no set answer that we, from a GC manufacturer, will tell you. I can tell you, though, you can, within the GC, set up the calibration cycle per your requirements to do it automatically. A couple of other ones. Do you plan to go over forced calibration, and when is it necessary to perform them? We're actually not going to go over that. Again, we have a topic on June 12th where we talk about calibrating your GC, and that's really a good one where we'll talk about when is it okay to do the forced cal. And generally I will tell you, don't do it unless you know why you're doing it. So there are times when it's acceptable, but you have to understand what you're doing when you do it. Okay. Well, there's a lot of questions. So I'm going to actually just kind of go through this and then try to answer some of these questions at the end, or we'll never get off this slide. So again, this is a really good, the final calibration report is really good to understand where the response factors are. So this is the first thing you want to look at, and most important is the order of your response factors. Again, because the list will be in order of elution instead of the carbon number, or basically the response factor size, you might have to kind of look at it yourself at the time. Obviously, we have some plans in the works, and if you have our 370, we'll actually put on that final calibration report, we'll actually put the order of the response factors, and we do have a alarm in there that if the response factor order is out of place, it will alarm. On our 700 XAs and our Model 500s, we don't have that alarm system or that capability today. That's obviously something under consideration. But if I look at the report and I look at, again, this is a C6, my methane through my C6 plus, the delta in thermal conductivity from low to high, methane would be the lowest, going all the way up to C6 would have the highest delta. And if I compare that against my response factor order, you can see they align, and that's actually a good sign. It doesn't mean everything is good, but it is actually a good sign. That's how we should match. So things look good. So another question we may have, because one thing we've noticed is we always talk about C6 plus when we talk about response factors, that some people may think it doesn't work for anything that's non-hydrocarbon, and that's not true. We just always, again, pick C6 plus because it is a simple application with a lot of components being looked for. But here's an example where we're actually looking for argon, nitrogen, and hydrogen. This is a gas processing application. It's about 3 minutes long using our 700 XA, and it's basically uses 4 6-port valves. It has 2 sample loops and 2 TCDs. And the reason for that is you notice that if you look in that first column under thermal conductivity, you have a range in thermal conductivity. So argon and nitrogen have a low thermal conductivity, while hydrogen has a high thermal conductivity. So what that means is that I have to use different carrier gases to do the analysis, and that puts me right now then into 2 detectors. So I'm going to group together the 2 that with the low thermal conductivity. So argon and nitrogen are going to go across 1 detector with the carrier hydrogen. Again, because hydrogen has a high thermal conductivity, that's going to be my choice. Or if I'm now, since I'm looking for hydrogen as well, and that has a high thermal conductivity, I need a lower thermal conductivity carrier. In this case, I picked nitrogen. Again, you would never use nitrogen to detect nitrogen, nor use hydrogen to detect hydrogen. One, you wouldn't see it because you would have no delta in thermal conductivity. So then, next thing you know is the delta, and you will notice that both the nitrogen to hydrogen and the hydrogen to nitrogen have both the same delta in thermal conductivity, but different response factors. So the nitrogen response factor is 1.4 to the power of the 8th, and hydrogen has a response of basically a 4.8 power to the 7th. And there's a reason for that, and there's a reason why we've kind of broken out the comparison, that we're only comparing argon to nitrogen and then hydrogen by itself, is that when you're trying to do the comparison on response factors, a critical thing that sometimes gets glossed over is that you need to have the same sample loop, the same flow path, and the same detector. So that is why hydrogen and nitrogen aren't compared to each other, and why their response factors vary. Because the flow path is different, they're using different valves, they're using a different carrier, and they're using a different thermistor. Okay, let me see, why couldn't you use healing carrier for the specific? You could probably use, instead of using hydrogen, you could have used that for the argon and nitrogen if you wanted to. You couldn't use helium for the hydrogen because they have very similar thermal conductivities, but it is possible that you could have used helium for the argon and nitrogen if you wanted to. Okay. So again, as I mentioned, response factors, you must go through the same flow path, detector, and the sample loop. Okay. So the next question is, we talked a lot about response factors working with an FID. With the TCD. Now can they work with an FID? So I'm going to give you guys a few seconds to look that over and just answer. While you guys are thinking about that, I will try to see if I can get through some of these questions. Okay. So one of the questions while you guys are thinking about your answers, how much of a variation of the carrier pressure affects the response factor? It actually does have an effect on it. And so we do show a formula later on about the variation in carrier pressure. And I should say it affects the variation in carrier pressure. It's really, the carrier pressure actually has more an effect on how quickly your sample comes out, because if you increase the pressure, things move a little bit quicker. So the impact it can have on the response factors is that your valve timing will be off. It's more variations in the atmospheric pressure or your sample pressure that can affect, everything else being constant, that can affect your response factors. But response factors can be affected indirectly, that if you increase your carrier pressure, you increase your flow, your valve timing may not align with the way it should. Yeah, so one of the questions was, can you miss a response factor shift slowly over time when calibrating daily causes mismeasurements? So yes, that's true. If you are calibrating because the GC is making some compensation, that if you're calibrating daily, you could miss subtle changes. That's one reason there's a webinar called Validating Your GC, that we tell you to look at your data over a 30, 60, 90-day period, because those subtle shifts, if you're calibrating data daily, won't be caught necessarily. And so that's why we do say you need to validate your GC every to ensure proper operating order. Somebody did have a question on what's the benefit of AutoCal. Well, the benefit is that you don't have to remind yourself to do it. The machine does it automatically for you. It's consistent versus you having to remember to do it at the same time every day if you want to. So it's just an ease of use feature. We'll talk about that more in the next webinar. Okay. So I'm going to go to the next slide and see the results of the poll. See if it popped up to you guys. Yep. So, yay, good. Over 60% of you realize you can use it with a FID, and that's correct. So, like I said, we do spend a lot of our time talking about TCDs, and it really is because we use C6 a lot. It's the one that most, these natural gas specifications are written around. We always talk about that 45 line that everything kind of goes on. And that's true, but it works just as well with a FID. So slightly different though. So with a TCD, we're looking for the difference in thermal conductivity. With a FID, we are looking for the number of carbons. So the principle employs that the electrical conductivity is proportional to the concentration of the charged particles within the gas. For a FID, separated components come out of the columns. They then get mixed with the hydrogen and are burned, basically either in air or oxygen. Ions are formed in the flame, and there's that electrical gap, which is basically, if you look at the collection plate in the figure on the bottom right, they say that's electrode gap, which causes current to flow across the gap through a series of resistors. That results in a voltage drop. So similar to the voltage drop we get with a TCD when the Wheatstone bridge is unbalanced. So we're getting that same type of voltage drop. And of course that creates a signal, and that signal is a peak error. So very similar to a TCD, except for instead of looking for thermal conductivity, we are looking for the carbon count. So in application above, this is alcohols and ethylene. So this is basically a 3/6-port valve application. Nitrogen is the carrier, and it's basically a little bit under 6-minute analysis. So you can see in this case, the components of interest do not equal up 100% because we are looking for impurities in ethylene. But it does show you again that you can look at response factors to make sure everything is looking good. So if I go to the next slide, I said we are looking for carbon count. So the second column is basically the formula for methanol, acetone, and ethanol. And so methanol has basically 1 carbon, acetone has 3 carbons, and ethanol alcohol has 2. And so if you match that up, so methanol having one carbon, and the smallest amount of everything on this, its response order should be first, and it is. Acetone, why it's the second component to elute, it actually has the most carbons out of the 3 of them, and so its response factor should be the largest or the last, and that is correct as well. It's 1.4 to the 12. And then ethanol alcohol, ethanol is basically 2 carbons, and it's in the second one. So we can compare these all with this fit is because they're all going through the same flow path, detector and sample loop. So if this was different where we had one on one detector and the other two another that we had in the previous version of the gases, we could not compare them against each other. But if we look at this, everything looks really good. And so again, a fit is a little bit different. We look at carbon count versus thermal conductivity differential. Okay, so we've kind of made it through half the presentation, and so I just want to try to see if I can catch up very quickly on some of these questions and see where we are at. Okay, let me see if I have, what effect does, so one of the questions is, what effect does response factor deviation have on retention time? For example, the slide showed an RF deviation of 0.6 and a retention time deviation of 0. So the response factor deviation is really more the change in the response factor. And so the response factors are impacted by the peak area as well as the peak area, well, the concentration. So again, it's not a direct correlation. You could, if your retention time shifts, say again, we go back to that example somebody asked about if you increase the carrier pressure. So you increase the carrier pressure, your retention time will shift, and it will shift out, right? Or I should say, it actually will pull in. If you're rushing it through, things will come out sooner. And so what could happen, again, it goes back to then your valve timing is going to be off. You're going to be cutting off possibly some of those peaks. You cut off some of those peaks, that it's going to impact you basically, if you're calibrating, it will affect your new response factors. So it's not directly, you could actually have a shift in retention time and not have a shift in your response factors because you're not affecting basically the peak area. So that's kind of, like I said, it's kind of, it can affect it, but not necessarily. It all depends on what that shift in retention time is doing. Okay. Should the sample pressure and calibration be the same? No, and actually, well, okay, so the sample pressure and the calibration pressure will be the same. Yeah, so we will tell you the sample pressure, most of our GCs is under 30 psig. That actually should be the same as the calibration pressure, because if you think about it, the calibration is really a known sample, right? So you really want them set to be the same. Obviously, that may not always happen, but you do want them to be basically, we always say between 20 and 30 psig for most of our GCs. You do want them the same because, again, you're comparing a known sample, aka your calibration gas, to an unknown sample. Basically, that's your process, your sample. Now, I will tell you, in our GCs and actually in the competitor GCs as well, that there's about 5 to 8 seconds in the beginning of the cycle that we vent to atmosphere. So that actually, it does adjust to variations in sample pressure, aka variations in carrier pressure, and it can make some adjustments. If your carrier pressure or your sample pressure is too high, above, so you get too much above that 30 psig, it may not be possible to completely vent to atmosphere, but the reason we vent to atmosphere is that we always have kind of the same reference pressure, because again, pressure equals V equals nRT, and we'll kind of go through that in a few seconds, but you do kind of want to have your pressure Consistent? No. A change in pressure will impact your response factors. Let's see. So I did just a quick question. The presentation is very helpful. Will the presentation slides be available for review later? Yeah, we'll work on that. If short term, when we post this onto the external Emerson site, we'll have the ability to download the presentation. But if short term, if you want to get a copy of it, because it does take a bit of time to get it on the website, you can send a request to analyzers@emerson.com, and we'll get you a copy of the presentation. It will be PDF versus the actual presentation, but that is possible. What can cause the shift in day? So I get what can cause the retention time to shift in day and night cycles. That one, I'm going to have to look into your particular application. If you're seeing a shift in retention time between day and night, that to me, I could think, well, that one I'd have to look at because there could be a couple of issues. So that would be one we would say, send us your diagnostic data tool so we can look at that. There'd be a lot of other questions I would start to ask you about what could possibly be why you're shifting retention time. So that shouldn't happen regardless whether it's day or night. What's the maximum sample gas pressure? Again, I think I mentioned that, but it is 30 psig, generally for all our GCs. You can find this information specific to your application. It's a process application. You'll get a parameter sheet that is loaded onto the GC, and that should give you the information that you need. Also, on the more generic applications, the information should be able to find in our manuals, which are located on the Emerson external website. Okay. We'll answer that in private. So I'm going to go on to the next section. So we kind of had a question about this. How does pressure affect your response factors? And it does. And so we'll hear at the end, but there's a couple things on our hip parade. Response factors is one of them, and unnormalized total is actually, and that actually relates to pressure. So when we did the analysis, a sample is injected, and it can be affected by the atmospheric pressure. So think of your storm fronts coming in, how that changes your atmospheric pressure. So you could, decalibrate your GC on a beautiful sunny day, and then a storm front comes in when you're running your analysis, and you're going to have a slight change in pressure. Because the sample loop is fixed, it's basically a piece of tubing, so it's fixed. If you look at the equation, PV equals nRT, we can assume the temperature is going to be fixed, that we're not keep shifting the temperature of the oven, so that's fixed. R is a constant. So if V is fixed, R is fixed, and T is fixed. If T varies, goes up or down, then N, which is basically moles, is going to vary as well. And so if your moles vary, that's basically your amount of sample. So if P goes up, you have a high pressure, you're basically squeezing more sample into that sample loop. And so you are going to see an increase in your concentrations, but everything should increase. It isn't that it just, the methane increases, but not the ethane. All the components' concentrations will increase proportionally to the increase in pressure, vice versa, that if you have a pressure drop, you're going to get less compaction into that sample loop, so you're going to get less sample, and therefore you're going to get, everything will have a lower concentration, will be shifted off. And that's where we're talking about the unnormalized total, and that's really where you're going to see that information as well, but it will affect your response factors. Other things that affect your response factors is basically degradation of your detector over time. It can get contaminated, it just kind of wears out, and so these definitely happen over time. But the thing to keep in mind is that all the components, all the response factors should shift. So if you have a trend over time, and you can see the new responses versus the old responses, there are shifts, but they're proportional. One shouldn't shift more than the other. It's that shifting of one response factor more than the others that give you a clue what something's going wrong with the GC. So because of that, sometimes to make things easier for people, we'll talk about the relative response factors. And what that is basically the response factor of a component A, whether it's methane, ethane, etc., over the response factor B. And that's another component that's of interest and that you're measuring the response factor of. And so a lot of time for a C6 application, the response factor B will be the methane. So everything is comparison against the response factor, or the ratio against the methane response factor. And because that kind of helps out a bit. Now again, it's the same rules. To compare one response factor to the other, they must go through the same detector, same sample loop, and the same flow path. And the reason we actually like relative response factors over just the straightforward response factors is that they don't shift. Because it is a ratio, if you plot the old response factor on top of the new response factor line, they should overlap each other. Where sometimes when you're plotting the old versus the new, you'll have a shift, but sometimes it's hard to see if that shift is equivalent. If you do relative response factors, it's much more of a clearer indication of any measurement issue. So I think we have a few slides on that. So again, this is a good looking C6 plus. So reference means basically the old response factor. Latest, the green line, means the new response factor. So in this particular one, you can kind of see that there's been a shift, but it's proportional for all the components. In this example, you'll see that the reference, the old, is to stay the same, but the latest or the new response factor, there's a shift in nitrogen. Now in this particular case, this kind of goes back, if we looked at one of the specifications, this would be your sample system in terms of we have a nitrogen leak. Nitrogen in the atmosphere is a higher percentage than generally in a C6 application. And so that leak would actually show up on a high peak for the nitrogen. So we can kind of see the peak, and it does show up when we're looking at the response factors. And one thing I should note too, it's not the response factors that we plot, it's the log of the response factors that we plot. But if I do it on the right-hand side, you can see the relative response factors, and you can kind of see how the reference and the latest, so basically the old response factor and the new response factor, pretty much overlap each other, except for when you're looking at the nitrogen. That nitrogen really sticks out. And it would stick out more, be more noticeable, say the gap, obviously these are slides, so we kind of make the worst case scenario. If you had a leak that wasn't as great as I'm showing here, it may be harder to see when you plot just the log of the response factors, but if you do the plot of the relative response factors, it would be much more noticeable. So again, we can also do this with the calibrations for the FID. So again, on the left-hand side, we're showing a perfect shift. It's proportional. It's what we would like to see. On the right-hand side, we're looking at something where the acetone latest or the new response factor is below that of the previous. And so in this particular case, this problem happened because of the time event. Basically, the inhibiton is cutting off the peak of the acetone, so the peak is not, the full amount of area is not being calculated. And that will cause the response factor to decrease. So if we did the relative response factor plot, it's really dramatic. So you can see on the left-hand side, you definitely can see that drop. And again, these are examples, so we tried to be a little bit more dramatic than you'd see in real life. But if you look at the right-hand side, we're plotting the relative response factor. We got a one-on-one from methanol and ethanol, but when you get to the acetone, it's very clearly gap that you can see. And again, I'll just remind you guys, it has to go through the same flow path, same detector, same sample loop. Okay, so we're going to kind of get into examples. Again, we're going to go back to the C6 because it gives me a lot more components to work with that go through the same sample path, same detector, same sample loop. So this one you can see quickly that N-pentane is below, it is not proportionally shifting. And so that's kind of like the first thing. So the first couple things I notice is basically the response factor of N-pentane is below basically all the butanes and the other pentanes. So it quickly tells me that's one area I'm going to start looking at. I can also look at, and we had this quick question earlier about response factors ratios and they're important. If you can look at that, So it tells me that it's not just N-pentane that's out of sync. It also tells me when my C6 is out of sync. And so that kind of helps you narrow down, so it's not just an N-pentane issue. I have another issue going on. So then I thought to myself, okay, what could cause those two to vary? Well, if I pull up chromatogram as well as know my flow diagram, so it's not just having your final calibration report, but some other documents as well. And so knowing my flow diagram, and I know when my backflush valve switches, it's really breaking the pentanes from the C6. I'm backflushing my C6 out. If that valve switching happens too soon, my pentane is not able to fully get out of column 1 before I start doing the backflush. So what's happening is that N-pane that I've kind of cut off is giving me a lower peak area for my N-pentane, but it's also giving me a higher peak area for my C6. So I would see that on the chromatogram in terms of my peak would be bigger for my C6 than I would normally anticipate. Obviously, also just when I would pull up my analysis report, I would see a higher concentration as well. But it's understanding my flow diagram that really helps me narrow down that it's a timing with the valve issue. In this case, the CO2 is higher than expected. It didn't shift correctly. It's out of alignment. So if I look at that, I can definitely tell my CO2 is higher than my ethane, so it's kind of off a bit. But everything else looks good. So I don't have an issue with one of the other numbers. So my odor is out. But the one thing I also need to look at, when you think about, again, I'll pull back my chromatogram, the order of elution is basically nitrogen, methane, carbon dioxide, and ethane. So that tells me right away CO2 is in the middle of that elution, so it's not going to be a valve timing issue. So I can eliminate that right away. So then it goes down to where I want to start to look. And in this case, it's leading me to the idea I did a fat finger. I put the wrong concentration in. And so I would go back and look at my certificate value compared against that first, or I should really say the second column on my final calibration report to see if they match. I could also pull up the component data table to see if my certificate of analysis from the calibration bottle matches what I put in the component data table. So this is just an example of somebody fat fingering something or basically typing it in correctly. In this example, ethane is less, than we anticipated it to be. So I can pull this up. Again, response factors a bit out of order. Ethane is smaller than CO2. And then I can look at my relative response factors, and I can see there's definitely a shift. But I'm looking after the other components, and I can see that propane, which would be when we do the valve timing, it's ethane is split from the protein. That's propane. That's the shift of the valve. But protein looks fine. So my ethane isn't short because I put more into the propane, or basically I shifted too early. So that tells me it's something more specifically to the ethane. Well, understanding my chromatogram and looking at how the valves work, what I would pull up and I would zoom in on my chromatogram, and I could probably find out in this particular example that my inhibit on is aligning with the end of the integration peak. And so when that happens, it basically means I cut off the integration of the peak. If I cut off the peak area, make it smaller than what it's supposed to be, that's important, right? The peak area was the numerator in the calculation of the response factor. So if that's not what it should be, then that's going to give me a reduced response factor. So that's kind of some of the examples that we had, or closely at a time. So I want to just quickly, going to show you a summary of this. Response factor is peak area of calibration concentration. Again, we can refigure that formulation when we're doing an unknown so that the concentration is equal to the peak area from the GC or the signal divided by the calibration response factor. Again, it works for a TCD based on thermal conductivity differential, as well as SID based on the carbon count. Regardless of which detector you use, if you want to do the comparison of response factors, it needs to be through the same sample loop detector, and flow path. Absolutely critical. Sometimes it's easier for you guys if you plot the relative response factor, which is basically component A over component B. You plot those because relative response factors don't shift like response factors can do over time. And again, if you do see a shift in response factors, it should be proportional for all products or all components of interest. If it's not, that's where it ties you in to what's of interest. So again, this is the hit parade. I do want to give credit out to Ron Lassiter. These are really words to live by. Before you start trying to fix your GC, ask yourself, what am I doing and why am I doing it? I did hear from somebody else today, a favorite line of somebody else was, don't contaminate my crime scene. So don't start changing things. If you want to understand what the crime was, you need to leave the situation as you found it and analyze what the issue is first before you start making changes. So the hit parade is response factors. Second one is unnormalized total, and that goes back to that pressure changes. And then the running the calibration gas is an unknown that will be talked about on June 12th when we talk about calibration gases. I think most of you guys have figured this out based on the number of questions I have, but if you guys still have questions, feel free to put them into the panel. I will try to get to as many as I can. This does conclude the presentation, so I do thank you for your time. We do have a few more webinars coming up for the year. Again, June 12th, I think I've beaten this one to death, but we're having the calibration gas webinar. The 12th of September, we're going to walk through the chromatograms and the telltale signs of a problem. You know, so what happens when you have moisture? What happens? How can you tell when you have contaminated carrier gases? And then I think one that's probably of most interest to a lot of people, FID and FPD and troubleshooting and hints. I know sometimes those detectors can be a bit finicky, and so we will give you some advice to make them a little bit easier to work with. And again, if anybody, if I don't get to all your questions before time runs out, you can send them in to analyzers@emerson.com. Same thing if you need to have a copy of the presentation before it's available on the website, you can send your request to analyzers@emerson.com, and we'll get you a PDF copy of the presentation. Let me see if I can get some of these unanswered questions that I might have. If the response factor is high for nitrogen, where would you start investigating the leak? Is it at the common places where a leak might form? Yeah, so if you were having a high leak, so the first thing I do would be the connection. So externally to the GC first, right? And so if you had just changed your calibration bottle, obviously those connections would be the first ones I would check. And I will tell you, when you do our automatic calibration, we will run the system 3 times trying to get the nitrogen value down. But that would be the first place. If you, I would check fittings areas are the most common. So logical thinking, yeah. So start outwards and work towards the GC would be where I would talk and do that first. Let's see. Okay. I have several different. Okay. So this is not kind of related, but I have several different heavier hydrocarbons. Am I correct that the C6 plus category will not necessarily be enough information for accurately estimate hydrocarbon dew point? Absolutely correct. It's not related to this topic, but trying to calculate hydrocarbon dew point from a C6 analysis, you basically have just as much chance of randomly guessing what your hydrocarbon dew point is. The accuracy absolutely goes up much, much more when you have a C9 plus. You definitely need to know what C6, C7, C8 you have running. So definitely do not use a C6 plus. We have some data sheets and application notes on that to show you the huge error rate if you're trying to do it with a C6. Okay. In case of liquid calibration, vaporizers would affect, the vaporizing condition would affect the RF or not. If you're vaporizing the GC, so it's going into the gas, if there's an error in your vaporizers, you're basically fractionating your components. Yeah, you could, because you're affecting the concentration. You could have dropout, so therefore you're not getting the concentration you'd expect. But you would see that result. You would definitely see a shift in your response factor, but you'd also see a shift in your concentrations, and that would be because if you did it correctly on the calibration, but you did it incorrectly when you do your unknown sample. Okay. Can the GC tell me the water content? It can. We do that. We don't do it with our C6 Plus, our standard C6 Plus. We can do the water content. It generally requires we will do a different detector, an extra one, so a 2-detector analysis, and we kind of more do it through a methanol analysis, so an inferred measurement based on the methanol. So we can do that. Definitely, that's something you want to contact your Emerson field guy about, but that is something we definitely can do, and we actually do somewhat on a relative basis. Now, I should also say it does depend on the concentration level. Obviously, we'd expect you'd have to be, above 3 ppm for us to be able to detect it with a TCD. I'm just trying to, there's only like 15 questions, so I am trying to get through them to see which one. Okay. Okay, do I have to register for the other webinars, or we register already for taking this one? No, you will have to register for the other webinars. The good news is that if you registered for this one, you will get an invite to the other webinars. I will tell you, in 2016, the last time we did these webinars, we did a mass mailing that you could register for everything at once, or you could do one at a time. We had a bit of a hiccup with the system when we did it that way, plus some other things that didn't go necessarily well and became an IT issue. So we are making people register individually for the webinars. It's a cleaner process, trust me. And when you do get the invite and you click on it, if you've already pre-registered for a different one, your field should automatically auto-fill in. You just have to then just click send. But it is, everyone does have to do individually. So how is the relative response factor and the ideal relative response? So they're calculated the same way. The ideal relative response factor is basically based on your reference or your initial response factor. So that's how, so they're exactly the same thing. The ideal is just what you expect it to be. Relative response factor is what it actually is when you run your unknown. So they should, your known and unknown should align. If they don't, that again is where you have a difficulty, but they are actually calculated the same exact way. It's just a difference that the relative response factor is based off of an unknown. The ideal will base off of what you anticipate it to be given using the same GC, same flow path, same detector, same sample loop. Okay. What was the email to send for a copy? Okay, that was already answered. So any more questions? We went a little bit over, so I'm going to end the webinar. I know there was a few questions that were a little bit off topic here that I'll probably answer, try to get back to people privately. Again, if you want to contact us, Emerson, it should be at analyzers@emerson.com. Again, I thank you guys all for joining. If you want to see this presentation again, you can use the link that you registered for, or we also will be sending out the link when we load it up onto the Emerson website. So again, thank you very much for your time today.